So now we're going to look at the development and the use of the scientific method to describe what we view today as the structure of an atom. So just remember the points or the details of the scientific method. We identify a problem and ask a question. We form an hypothesis. So this is an educated guess or a tentative explanation that describes or answers our question. We design and carry out experiments. We record the data and observations and then draw conclusions. And as we look at the development of our understanding of the atomic structure of an atom, we will see this method at work. So long before a man named John Dalton proposed atomic theory in 1808, Democritus, a Greek philosopher from the 5th century BC, so this was somewhere between 460 BC to 370 BC, was the first to suggest that matter was composed of indivisible particles, and he called these particles atoma, or indivisible units, from which, and the atoma is where we have derived the English word atom. Okay. So for the smallest indivisible unit of matter. In the 19th century, John Dalton formalized the atomic theory, which is composed of the following hypotheses that describe the nature of matter. But think about this. 2,000 years later, it took 2,000 years for that idea to gain support and scientific evidence that the atom was the smallest indivisible particle of matter. So the components of the theory, which is designed to explain the structure of an atom, are as follows. Elements are composed of extremely small particles called atoms. Okay, everyone agrees upon that. The second statement, all atoms of a given element are identical, having the same size, mass, and chemical properties. The atoms of one element are different from the atoms of all other elements. And while most of this statement is true, this part of Dalton's atomic theory had to subsequently be amended. And here's where we're going to see that scientific method in play. So we now have the understanding that not all atoms do have the same mass, because there are isotopes of atoms or elements. And we'll talk more about those later. Compounds are composed of atoms of more than one element. In any compound, the ratios of the numbers of those atoms of any two elements present is either an integer or a simple fractions. So basically, all this is saying is that atoms of one element can combine with atoms of another element to form compounds. And the last statement, a chemical reaction involves only the separation, combination, or rearrangement of atoms. It does not result in their creation or destruction. And this basically comes from the law of conservation of mass, which states mass can neither be created nor destroyed. This also indicates that atoms can't be created or divided into smaller particles, only rearranged. Now keep in mind, I think I've already said this before, that, well, we know we can break atoms into subatomic particles. That requires a nuclear reaction. And we are only focusing on a chemical reaction here, which the atom then is the smallest indivisible particle. All right, so I mentioned the law of conservation of mass, and this is a diagram or a pictorial diagram of what that means, where we have atoms of element X reacting with atoms of element Y in a 6:8 ratio to produce a compound that contains both elements X and Y. And you'll notice that whether you count the numbers in these pictures or add the numbers on each side of these equations, the chemical equation, we will have the same number of X and Y atoms on either side. So again, that fourth statement in Dalton's atomic theory is derived from the law of conservation of mass. This comes from what's called the law of multiple proportions. And so this refers or is the founding argument for Dalton's third statement in his atomic theory, and that is that the ratio of the numbers of atoms is either in an integer or simple fraction with respect to composition. So when two elements combine to form more than one compound, and the example used here is carbon monoxide versus carbon dioxide, the masses of one element which combine with a fixed mass of the other element are in a ratio of small whole numbers. So now we're going to take a look at some of the experimental evidence that supported the development or the further modification of our understanding of the structure of atoms. And J.J. Thomson was utilized, I should say, the cathode ray tube to determine the charge to mass ratio of an individual electron. Okay, so he discovered the electron and then he measured, using the cathode ray tube, the charge to mass ratio. And so this is a diagram of that cathode ray tube, and we've got a voltage source, we have the cathode, an anode. This is a stream of electrons, or what was learned to be electrons. We have the charged plates, we have a minus NO plus charge, and we have a magnet as well. So the cathode emits, as I said, an invisible ray that's drawn to this positively charged plate, where it continues to pass through a hole to the other end of the tube. Okay. And then we have this fluorescent screen here. That ray then strikes this specially coated surfaces and produces a bright light. Okay, so when and these charged plates are outside the cathode ray tube, and of course the magnet's outside as well. When the magnet is on, the particles that are streaming here, which we now know to be electrons, strike the screen at position A. So the magnet's on and these electrical plates are turned off. Okay, so this is a deflection away from the southern pole of this magnet. When the electrical plates are on and the magnet is off, then this stream of particles hits at position C. And so that's a deflection of away from that negatively charged plate. And we know that opposite charges attract, but like charges repel one another. So this, based on the evidence and the observations and conclusions from this experiment, the particles were negatively charged, and these were the electrons. So you should know that Thomson was credited with measuring the mass-to-charge ratio of the electron, and he did obtain a Nobel Prize for that work. You don't need to know years here or anything, but you should be able to associate the scientist with his experiment and what he discovered. So Thomson added to our understanding to the structure of that atom based on his cathode ray tube experiment, but he described the, amended the model somewhat. So it was accepted that atoms contained negatively charged particles called electrons, but the atoms themselves were electrically neutral. So Thomson proposed another model of the atom, which is sometimes called the plum pudding model. And he described the structure as positive charge uniformly throughout this sphere in which electrons were embedded. And that's a description of a famous, or a popular dessert, I should say, in England. So the plum pudding model was Thomson's model. Now there's another scientist, and this gentleman, wrong slide. Skipping ahead of myself here. They're not in the order I thought they were. I hope I didn't skip the gold foil experiment. I don't think so. Anyway, I'm rambling here. Millikan's experiment. Millikan is from Iowa, and he performed what's called the gold foil experiment. Or the oil, I'm not gold foil, that's Rutherford. The oil drop experiment. Sorry, got confused since the wrong slide came up. What Millikan did was measure the charge of the actual electron with great precision, and he also measured the mass. He used Thomson's work, or the charge to mass ratio, to do this. He also, let me pull some other data up here, received a Nobel Prize for this work. This is the charge that he determined using the charge to mass ratio and the mass of the electron. So anyway, in this experiment, we have charge plates, positive plate, negative plate. There's a small hole in this plate. There's an atomizer that emitted oil droplets into this container. and then a viewing microscope here. And what Millikan was able to do was adjust the charge from these plates to suspend an oil droplet in between the plates. And based on that charge, he was able to use Thomson's charge to mass ratio to determine the mass of that electron. All right, here's Rutherford and his gold foil experiment, which is what I thought was coming up next. That's okay. So another contribution to our understanding of atomic structure came from this experiment performed by Rutherford. He actually was worked with Thomson, so they were colleagues. I think at one point he was a student of Thomson's. Anyway, in this experiment, there's a radioactive sample in a protective box, but there is a hole in which the radioparticles can escape from. And the particles from this radiation or radioactive material are called alpha particles. And these are positively charged particles. In the center, there is a piece of gold foil. It's about 200 atoms thick. And surrounding that is a fluorescent screen. So the positively charged alpha particles are emitted from that box. They travel to the gold foil. And we'll talk about the numbers of, or give some numbers data in a moment. But there were three things that were observed. There were some alpha particles that went straight through the foil. There were some that were slightly deflected. And there were some that bounced right back. Okay, so these are where the alpha particles are hitting this screen. So we know the alpha particles are positive. So in order for those particles to be deflected, this one has to be getting close to something positive, since it just veers off slightly. This one is hitting something directly and it bounces straight back, basically. Most of them go straight through, no deflection, nothing. So it was proposed that atoms have a positive charge within them, and it is concentrated in the nucleus. So updating our understanding of the structure of that atom, we now have identified the proton, or that positive charge. It has a +1 charge, and the electron is a -1 charge. And he was also able to determine the mass of that proton, which is 1,800 times larger than the mass of an electron. So for our purposes, we generally, when it comes to describing the mass of a proton and electron, we say that the proton has a mass of 1 atomic mass unit, and because the mass of the electron is so negligible, it has no mass. So Rutherford's model then, and even though those diagrams shows neutrons, those weren't yet identified, basically indicated that in the core of the nucleus, or in the core of the atom, we have that positively charged nucleus that takes up very little space in comparison to the actual volume of that atom. So the nucleus is very, very small in comparison to the size of the atom itself. is positive and it's positively charged. So a gentleman by the name of Chadwick originally proposed a positively charged particle existed, but he had not been successful in proving it. However, he is responsible for identifying the neutrons that are in the nucleus. And he too received a Nobel Prize for this work. So, and obviously completed Rutherford's model, because this wasn't really part of that. So the question that Chadwick asked basically was, if a hydrogen atom has 1 proton and a helium atom has 2 protons, then the mass ratio between helium and hydrogen should be 2. So 2 divided by 1 is 2. We knew there was 1 proton in a hydrogen atom and 2 in a helium atom. But the measured mass ratio is 4. So how can that be? Where is that other mass coming from? There has to be something else there. And so Chadwick's experiment also utilized alpha particles, or alpha radiation, and he bombarded the beryllium atom with these alpha particles. And what resulted from that bombardment was a neutron, or this particle, and a carbon-12 atom, plus energy. So, here's what I was looking for. There we go. The neutron then was found to have 0 charge, so it's neutral, and it has a mass that is approximately the same mass as a proton. So that is what makes the helium atom has 2 neutrons, so that helps. Actually, it has more than that. Sorry, I'm helium. I'm thinking of beryllium. Never mind. Anyway, that's how the mass ratios become 4, because of the presence of those neutrons in the nucleus of the atom. Okay, so no charge, electrically neutral, but has a mass approximately equal to the mass of a proton. This is a table from your text, and it just summarizes the characteristics, or the masses and charges, of those subatomic particles: electron, proton, and neutron. You do not need to know masses in grams. We don't work with those. We'll work with atomic mass units, which will be introduced in Chapter 3. This is the charge in coulombs, but it's customary or more convenient to use the charge unit, which is just -1 for an electron, +1 for the proton, and 0 for the neutron.